All right, welcome to my presentation. It's not a bug, it's a backdoor. This is a presentation that I originally gave a few days ago at the All Things Open conference in Raleigh, North Carolina. And I'm re-recording it for YouTube just because I am not certain whether they will publish a recording of the original presentation. And there were a few slides that I had to kind of skip over or go through quickly. And so you can consider this the extended version. Now, the reason I'm putting this out there is because I'd really like to stimulate some more dialogue about how companies who are using JavaScript, and in a crypto context in particular, such as Bitcoin companies or companies that are producing, companies and projects that are producing JavaScript crypto code, we can start talking more about how we can identify backdoors, underhanded code, essentially, and new ways to identify and mitigate that stuff. So JavaScript and crypto. Let's talk about JavaScript first. So JavaScript has many redeeming qualities that make it an attractive way for companies to write crypto code. Now, for a long time, people were saying, don't use JavaScript for this. It's too flexible. It's too easy to make little subtle mistakes. And in some ways they're right, but there are some redeeming qualities that have led companies to do this. So JavaScript is web ready, right? If you write some JavaScript, people can easily execute it in their browser, and it's fast to develop. And writing JavaScript is just naturally faster. And also there's quite a lot of libraries to leverage at this point. One of the major key points there is, sort of on in the back end or the library end of things, you have things like Node.js, which led to an incredible explosion of libraries that are out there, including for crypto code, and also tremendous number of frameworks that make front end development very easy. And so, since in a cryptocurrency context, you want people to be able to hold their own private keys. That means that the private keys need to be generated on their own machines, whether that's on a desktop or laptop computer, or whether it's on a mobile device, all of which are capable of running JavaScript. And so this means we need to be able to do crypto stuff on these machines, and JavaScript is one way to do it. It's also very open source friendly. There's a huge open source community around JavaScript, and it is being used for password managers and Bitcoin wallets and things like that. Now, on the other hand, JavaScript is easy to obfuscate, and it's easy to sabotage because the language is so flexible. When something unanticipated happens, something unanticipated to the programmer or to the user, JavaScript tends not to throw an error and crash, but instead it will just implicitly cast things and convert and move on its merry little way. And maybe the most extreme thing is it throws some error in the JavaScript console, which the majority of users are not going to even bother looking at. So that's kind of a challenge for code that has been subtly modified or written in some subtle way. So today we'll talk about how to sabotage code in JavaScript with an emphasis on crypto implementations, and how to mitigate these kind of attacks and how to prevent them. Say we're looking at some crypto code in JavaScript, what kind of stuff are we going to expect to see there? Well, there are a few things that you tend to see in crypto code in general, right? So in this screenshot here, this is an excerpt of the AES implementation in the Crypto.js library. And some of the things you'll notice here, you do see a lot of loops, and that's typically because you're operating on like blocks of data at a time. You'll see a lot of magic numbers, and that's maybe a magic number that the cryptographer came up with that somehow helps to obfuscate data to make it difficult to reverse. Or it may be that the number helps operate on a particular chunk of memory at a time. And if you look at this AES implementation, particularly on the section here on the right, lines, for example, 47 through 52-ish, some of those numbers have to do with operating on particular sections of the data. You'll also see a lot of arithmetic, and you'll see in particular, a lot more bitwise arithmetic in crypto code than you might see in other kind of JavaScript stuff. And this is the typical way in which crypto algorithms are being expressed. Some other things that you'll also typically see, this is not a comprehensive list, but some things that are not shown here, but you'll often see are functions to do with encoding and decoding of data. So for example, if you had a Unicode string that you wanted to encrypt, well, you need to be able to do that in some standardized fashion. Likewise, you'll also see a lot of functions related to padding of data to make sure that things are sort of the amount of data that you're expecting to see, both before and after things are encrypted and decrypted. And this all has to do with standardization. You need to make sure that one person's AES function works the same as everyone else's AES function. So to get us started, let's look at an example. This is, we're going to start with a C++ example, but we're going to quickly see how it would translate over into the JavaScript context. So this is a pretty famous bug. This came up in the last year or so, and this was known as the Goto fail bug, right? This was in the iOS operating system. And so this is in the SSL key exchange.c file, which is open sourced. And if we look at this code, the bug here may not stand out to you immediately, but if you look more carefully at line 630 and 631, you can see there's these series of if statements, and if there's some checking for something, and if there's an error condition that's met, then you're going to skip to a label called fail. And which involves freeing some memory and stuff like that. And you don't want to prematurely free memory because otherwise bad things can happen, and that's what happened in this case. So on line 631, you have this second Goto fail statement, and it's indented the same way as all the other statements, but actually it has nothing to do with the if statement above it, right? So line 629, if whatever. Then 630 is part of, it's the then portion of the if then go statement. And then the line after that is unconditionally executed if you get to that point in execution. If none of the prior conditions are met, then you'll always end up going to fail. And this caused some kind of terrible memory problem in their application. It was a pretty major zero-day vulnerability. Now, this probably would have been caught by what we would call a Lint application or a Lint compiler. So a linting application is a kind of compiler that has a very specific understanding of how code ought to look. Regardless of what a programming language is fully capable of doing, it has a specific constricted understanding of the way that it should be shaped and what elements of the language are being used and so forth to kind of standardize things. And in this case, it probably would have complained, we'll see this in the next slide, but it probably would have complained that this second Goto fail statement on line 631 is indented as if it was part of some larger block of code, when in fact it's not actually being executed in that context. So here's what it might look like if we translated it over to JavaScript. So in this case, I'm just calling a fail function, and since there's no sense of Goto labels in JavaScript, actually I have seen someone that wrote a way of doing that by using labels in comments, and then you would scan for the labels and run the code in this kind of massive eval statement, which is pretty ugly. I wouldn't recommend doing that. Now, if we run that translation into JavaScript, we run it through a linter and we resolve the errors until it's happy with what's left over. Here's what we might end up with. So the second excerpt down here towards the bottom, you'll see on line 20. Now the fail statement is totally not indented with the rest of the code, and it would actually be kind of tricky to figure out a way to somehow make it blend in better. So we don't know whether Goto fail, whether that bug was intentional or whether it was simply accidental. And that actually raises a pretty interesting question around underhanded code, right? So depending on the nature of the attacker and what they're trying to accomplish and what their relationship is with the organization that they're attacking and so forth, they may or may not want plausible deniability after the attack succeeds or is detected. So you could imagine maybe one attacker who gets into an organization somehow manages to compromise the code, whether that's, in some library dependency that they're using or whether he's actually working for the company. Maybe he steals all the Bitcoins and he absconds to some tropical island and no one can ever find him again. And so maybe he doesn't care about plausible deniability after the fact because it's already effectively too late. But on the other hand, the more common case would be that, the relationship of the attacker to the people who are victimized is that, they may be able to find him and track him down and do something about this. And so plausibility, deniability, it makes these kinds of attacks harder. It means that your attacks in underhanded code need to be more subtle and they need to look like plausible accidental bugs. So maybe we'll talk a little bit more about that in the future slides. So we can see that linting is an effective technique at thwarting some attempts at underhanded code. So let's look at a few more examples. The next series of examples is from submissions to a contest. And I'm going to start off with my submission to the contest. This took place earlier this year in 2016, and it was called the JavaScript Misdirection Contest. The purpose of the contest is to gather submissions on people, doing underhanded code, and the sort of description of what people are trying to do is imagine you are writing some code that takes input from a user. They type something into a box, and you have some kind of function, let's call it generate key. It's going to take the input and do something with it so that semi-plausibly it would turn it into a private key. And you can imagine the private key being used, for example, for a Bitcoin private key or some other cryptocurrency, where there's going to be money stored locked up using this private key, and so it's important for the private key to be secret and to be robustly generated and so forth. Now the contest did not focus on making sure that people were using like truly robust cryptographic methods, because that would really make the code a lot longer and more convoluted. So there wasn't really a focus on that. It was more to do with the underhanded stuff. And the goal was to generate a key that's being shown back to the user, but then is also being exfiltrated in some fashion back to the attacker. So starting with my example, we have here, if you look at my definition of the generate key function here on the left, what it does is takes the input from the user, and if they enter 2 or more characters, then it's going to pass that input off to a CRC32 function. CRC32 is a hash or digest function, not cryptographically secure at all, but I just wanted to keep it real short, and that's a function that can be defined pretty quickly, and then it returns the CRC32 hash. And if I remember correctly, it is, the code that I have does it honestly. It's the real, typical version of CRC32. Now over here on the right, there's this tiny screenshot. We're going to blow it up in just a moment so you can get a better look. But what I'm showing you here is in JS Fiddle, which is what we used to submit our entries for this contest. We can see a couple of things. Sort of on the left-hand side, there's my code. To the right of that, there's the area that's rendering the HTML and running the JavaScript. And you can see the user has typed in something. They've gotten some kind of key back. It's a bunch of numbers just to the right of that. And then over on the far right side, there is the network browser for Chrome, and it's showing suspiciously that there's some network traffic being generated as the user is shown their key. Now, if we zoom in just a little bit more, we can see that the requests that are being generated have an interesting URL. So we have a domain new val dash some numbers, and you can notice also that the numbers look similar but not exactly the same as the key that's been reflected back to the user, and .mydomain.com, and we can also see the full URL is /warning.png. All right, so let's take a look at what I did there. So there's a couple functions that I want to draw your attention to. We already saw the generate key function, and there's a few other functions here as well. There's a UTF-8 encode function. There's nothing interesting going on there. That's just a normal UTF-8 encode function that I took from some library. There's also above that, there's a global variable called arguments, and it's an array that starts out as an empty array, and I've tried to pass it off as just sort of a lazy thing. I wrote in a comment, fix me global variable, right? So at some point in the future, this is not a best practice to use global variables in this way, but I'll fix it at some point in the future. There's also two other functions. There's a get domain function, which we'll take a closer look at in a moment, and also the CRC32 function, which is computing that hash. And again, I think as far as I can remember, this is a truthful, honest CRC32 function. I want to draw your attention to a couple of things, though. So the first is the get domain function. So it takes a parameter called logster, and it says, okay, we're going to write that to the console, and we'll log it to the console for advanced users in order to review that. Okay, that's a little bit strange, but whatever. All right, and then it looks like after that, we're returning argument 0. Maybe that has something to do with the global variable. We're saving something in this global variable .mydomain.com. Okay, all right. And then in our CRC32 function, I want to draw your attention to sort of the middle bottom area, lines 90 through 97. There's this interesting if statement, which I've labeled in a comment as sanity check. And then I editorialized a little bit more. I said, well, this should be extremely rare, but let's display a warning to the user if something is sort of off here. And what I'm checking is there's a variable in the computation of the hash called newval. And I say, well, imagine if newval for some reason exceeded math.max or went under math.min. These are two variables that are, these are two values in JavaScript that have some significance in terms of their value. If you had a number that was not in that range, it would probably lead to some undefined behavior. So okay, that seems like maybe a plausible thing to check for, because you don't want to generate a broken random key, of course. So, and then it sort of looks like, okay, so we're going to show the user an image if this bad condition is met. Okay, so we call document.createElement, we're creating an image tag, and it looks like we are getting the domain for the image from getDomain. It's a static value, really, but okay, fine. I mean, this is a weird kind of kludgy way to do it, but not necessarily suspicious. And and I see the thing that we passed to getDomain was this newval value. So the idea being like, okay, so we were computing this thing, and something terrible went wrong with this newval variable, and then we're going to log that value to the console for advanced users to take a look at and try to figure out what went wrong. And then we're also going to show them a warning image of some kind using image.mydomain.com/warning.png. Okay, fine. Now, we know already, though, that it was creating these suspicious-looking network requests that really shouldn't have happened. So let's try to figure out what underhanded thing was going on. There's really two things here that were going on. So the first one is that it's this arguments variable. It turns out in JavaScript that arguments is a reserved keyword. And when you refer to arguments in the context of a function, it actually will, as a sort of indexed array, it will actually refer to the parameters of the function rather than anything outside of the function. So when I refer to argument 0 in getDomain and also in CRC32, I'm not referring back to the global variable that I declared on line 3, but I'm actually referring to the parameters. So with that in mind, we can see on line 93 where I tried to set argument 0 to image. Well, that's not setting the global variable. When I pass new val over to getDomain, I log it. And then when I call argument 0 there on line 31, I'm not actually grabbing the image string that I pretended to set on line 93, but actually I'm logging new val, right? Which was, I'm referring to new val, which is it's part of this hash that I'm trying to compute. It's an important piece of information, and if someone were to exfiltrate that piece of the data, they could easily reconstitute the rest of the hash in a deterministic fashion, some simple bitwise arithmetic to take the new vals and kind of put them back together to get the full CRC32 hash computation. And so actually the domain that we're referring to is going to be the private key, new val dash, as defined on line 96, the private key or something related to it, then .mydomain.com at warning.png. And that's being turned into an attempted loading of an image, which may or may not actually exist. We could easily set up our web server and our DNS server such that it captures this traffic, and we can either send back an image, like a transparent image, 1 by 1 pixel transparent, or we could not. But either way, it's actually not going to be shown to the user. Now you might be thinking, well, this is only going to be executed in extreme, unusual conditions, so what's the big deal? This is kind of a lame hack. Well, I've done one other underhanded thing, which is on line 91. When I compare new val, I compare it both to math.max, but not just math.min, but the parse float of math.min. And it turns out in JavaScript, when you parse math.min as a float, it turns into infinity. And so this if then block is always going to be executed because new val is always going to be less than an infinity. And so we're always going to create this image. We're going to exfiltrate part of the private key, and this won't be shown to the user. So this is how the full exploit works. Now, if we ran this through a linter, that would be the end of this attack because there's some things that just can't be fixed, right? So one of them is this arguments reference. So JS Lint, which is a popular linter for JavaScript, it knows that arguments is a reserved word, and so it complains about that. And likewise, when I attempt to refer back to arguments in these different functions, it says, nope, this is a named parameter. Don't do that. You're not supposed to do that. And when I pretend to set that global array, the first element to the image string, it complains about that as well because I'm sort of abusing this use of the arguments keyword. So that's the end of that exploit, right? If we had this requirement as an organization to only accept code that had been linted and was not throwing up any errors, then this wouldn't be able to pass muster. So let's take a look at some other examples that may be able to slip through that. This next one also would not be able to do that, but I think it's a very interesting example. This submission won the contest. It's very short. It's only maybe about 20 lines or so total. And one thing that's interesting about this is that when you look at it, it is obviously obfuscated code, right? There's no way that a reviewer would look at this code and think that this would pass muster as a legitimate way to generate a private key based on the user's input. And so it's not that helpful of an example to look at like very subtle underhanded code, but there's a lot of interesting things in JavaScript that this is taking advantage of. And so I want to go through a few of them with you, just so we can get a sense of how much can go wrong in just a short amount of code. So let's just focus on 2 lines, line 13 and 14. So just briefly, in the generate key function, we're getting some user input. It gets at least 10 characters, and then it's going to call the hash function based on the input. Line 12, the hash function, it calls the argument payload, and we'll see in a moment what's being done with payload. So all this text in red here is sort of my annotation of what's happening in just these 2 lines. So starting on line 13, we have a variable called hasher that's being set, and somewhat oddly, there's sort of this weird encapsulation of like, okay, so we're defining a function, and there's some reference to this, and that already seems a little bit odd. It seems like somehow we might be creating an object or doing something a little bit funky. We'll get into that in just a moment. There's also this suspicious looking hex encoded string, 49 D6166765. And if you take that and you decode it back to a standard, ASCII representation of the string, it's actually the word image with a capital I. So someone who is reviewing this code, if they bothered to notice these values were obviously hex range ASCII values, and they decoded it, got to image, they might be a little bit suspicious of that. Now note also that the image element of HTML is a common way that security people use in JavaScript and in websites to do sneaky things, to load external code for cross-site scripting exploits. And in this case, it's both myself and this person had the same idea to use the image tag to kind of quietly exfiltrate and make a background HTTP request to a remote server containing the key. Okay, so that's that first line. Basically, what's happening there is we have hasher equals new this image, which returns an image element via an implicit cast from string to creating an object. And so that's pretty interesting that in a single line you could take this hex encoded string and turn it into a real HTML element that can be inserted into the DOM just in one single line. Now 14 is even trickier, right? So the first thing to notice is this call to math.random. Math.random does not take an argument. Now JavaScript won't complain about that. It will simply ignore the argument. And so now knowing that, it's interesting to note that the payload parameter that we got, where that's supposed to be the user's input that we're doing something to, that's being completely ignored, and that's the only reference to payload in the entire function. So essentially, we're completely ignoring that user input. All right, so math.random is going to return a decimal kind of float value between 0 and 1. If you take a value like that and you do a bitwise XOR with a number, you're just going to get that same number back, right? So that hex number 9198, well, that's what the whole math.random call and XOR get resolved to. Now that leaves us with a number, and we're calling the toString function on that. If you look up the definition of number.toString for JavaScript, the argument that you pass it, if you decide to pass one, is going to basically be a number that represents the base of that number. Right, so you could have a base 2 number, base 3 number, all the way up through base 36, and that's how we're telling this function to sort of understand the string, or understand the number as we convert it to a string. And then we have another funny little thing. We have negative tilde 0 x23. And the tilde function or operator is this kind of obscure operator. What it does, it takes whatever number you pass to it, it adds 1 and then multiplies that by -1. I don't know why exactly you would need to have this, but this is an obscure thing built into JavaScript. So that whole thing resolves to the number 36. So we're using the maximum possible base number. So we have 91, 98, 98, and toString using base 36, and that turns out to resolve to the string src, and that's what we're setting the variable seed to. So if we see anywhere in the code a hasher.seed, or seed is some kind of subfield of hasher, we know that that's actually going to be image.source. And we can actually see that immediately on line 22, where you see hasher, the field seed, is being referred to. Now, there's a lot more that's going on in this function. I don't want to go through all the little details because there's a whole lot more detail to happening just in the for loop. But suffice to say, all the complicated looking stuff going on in the for loop, it ends up resolving to the following string, // and then some random digits, which are going to represent the private key that's being sent back to the user, and then .src.sr. And what's interesting about this thing is that // is basically like, okay, this is a link, and it's whatever protocol you're currently using now. So if you loaded the page on HTTP, then it would be an HTTP link. If you loaded it on HTTPS, then it would be an HTTPS link. So that's kind of like an abbreviation of that you can use for links. And then some src.sr is a legitimate domain name that you could register if you wanted to. SR is the TLD, or top level domain, for the African Republic of Suriname, which I'm probably mispronouncing. And so interesting that the string turns into a URL, and it's supposed to be it should be something that's related to generating a private key. So the fact that it's some weird URL is pretty suspicious. And the return statement is basically returning, new this image.source equals then the URL. And so what we're doing there is we're creating a new image element that loads that domain, and then what actually gets returned to be shown to the user is a slice of that, just the sort of number part of that. And so this is a tricky way of exfiltrating the private key that's being shown to the user as a domain that, and it kind of a clever way of constructing this domain. Just from the word source, you can also get the .sr, and using some obscure arithmetic. So this is a pretty cool and interesting example of all the stuff that you can do in JavaScript that's kind of tricky and hard to understand. It's hard to understand. This is the main thing about this example, is that it's hard to understand. This is one more thing that I wanted to say about this example, which is it's not lint friendly, right? So if you try to run this through JS lint, it will just explode, and it will be horrified. And so this would this kind of attack, it would need substantial changes in order to pass muster through lint. This is not a very realistic example of underhanded code. I would say it's very difficult to predict what's going to happen before actually executing it or stepping through it mentally very, very carefully with a careful understanding of what's going on in the code. One of the things that you would obviously have to change is that hex-encoded string of image. Lint doesn't like that type of string, and so you'd have to find a different way of representing that string. All right, here's another example that I think is really cool. This one was from Ephi Gabay, whose name I'm sure I'm butchering. Apologize for that. And I'm showing you here just a slightly modified version of his submission, which is more lint friendly. This one is completely lint validated, so lint wouldn't have any complaints about this. And the really cool thing that's happening in this example is it's taking advantage of the way that that JS Fiddle works. We submitted all of our contest submissions through the JS Fiddle website, which has a few boxes to it. It has I'll move on to the next screenshot here. It has not showing all of them, but you have a code part of the window. You have the HTML that you're going to use, the CSS, and then actually shown here we can see the results that's being rendered and the code is being executed. And the way that this is done by JS Fiddle is it has, before the user tries to run their code, a result pane. and that loads a kind of temporary iframe. And the iframe contains the HTML that was entered, and then it also kind of spits out the code that you wrote in this script block. And so with something going on in the code, I'm going to switch back once more to the code. There's on line 15, there is this reference to result span, which is the results area of the rendered window. And then we have next element sibling. And what that does is it says, okay, well, wherever this portion of result span is, let's like look at the next thing. What's the next part of it? And then it's matching something in there. And we have this regex string, 4 letters between A and Z, which, by the way, only matches HTTP, only lowercase, followed by colon, and then I've tweaked this regex slightly, but then it's basically matching this URL, which is contained as a comment in a very innocent looking comment at the end of the code, like, oh, this was coded by Ephi Gabay. My blog can be found here. It's like this nice, friendly little message that's put there at the bottom. But when it's executed, this regex is actually finding that URL, and then the following parts of the code are actually making a call, a surreptitious call to that domain and exfiltrating the key. And so I just thought this was such a clever way of accomplishing this where you're using the layout of JS Fiddle and you're grabbing the URL that you're leaking to, and from a comment. Because typically, if you're looking for underhanded code and you're looking for suspicious looking domains or whatever, you'd be looking at the actual contents of the variables and so forth, and you'll probably ignore the comments. It's pretty common that you'll see URLs included in comments to say, well, this is where you could find this script, or here's who wrote this or whatever. So I thought this was like a super clever way to do it, and really it's using that next element sibling function to focus in on something that's going in on the DOM to kind of self-referencing in a way that's not very obvious. Like next element sibling seems like a fairly harmless function that you may not pay very much attention to unless you're really looking at this in a detailed fashion. All right, so let's look at this example just very briefly. This is from Kamil Vavra, and I want to call your attention to line 18 with a variable called salt that's being set, and there's a string and it has some numbers. And the main thing that I want to say about this is that this is actually this number is an alternative representation of the IP address 127.0.0.1, and so that's how he chose to exfiltrate the key. So if ever you're trying to look through code and you're trying to look through things that look like some kind of weird domain or IP address or any kind of other way that you might be, the attacker might be in an underhanded way trying to leak data or pull down malicious code from an external source, you have to be aware of the different ways that people can represent domain names and IP addresses, both IPv4 and IPv6 addresses, and there's a variety of ways to do that. And this is one of the less known ways. And so the name of the game here is that we are using conventions that not all programmers are familiar with. Now here's a really cool example from Hahn. What I like about this example first is it's lint friendly. It's completely linted. I've just made just a few little tweaks to get it completely linted, I think, and it looks pretty plausible in the context of, okay, we're just trying to write a function that is taking the user input and is using some weak cryptographic function to kind of twist that input around and give something different back. This looks fairly plausible. You may have heard of the veneer cipher before. We have an array with a bunch of magic numbers, and okay, so this is some kind of like number pad, and we're somehow combining the input with the number pad. We see some modular arithmetic, and maybe it looks like maybe it's being somehow combined, the input with the veneer key, and then we're going to return the result. And the way that this is actually exploited is a little bit subtle. So one of the important things that is happening is on line 20, we have a for loop. And you might not notice this if you're kind of just skimming through the code, but if you're going through, if you're doing a for loop from 0 to some number for an array, and that's what input is I think is a string. And so we're going through the input one character at a time. You can see on line 21 we're saying char code at. So we're going to go from 0 to the length of the string. Now the subtle thing that he did was instead of less than, he did less than or equal to. And so that means that when you, for the final round of this for loop, when we do char code at, input.charcode at on line 21, it's going to return back a kind of null value because there's no character there. That's one past the end of the string, because we're doing a 0 index of the positions in the string. And so that means on the preceding lines that instead of grabbing something to do with the user's input, we're actually just going to grab the entire veneer key. And if you were to take the veneer key and convert these ASCII values, and you can look at it and you can see pretty clearly it's a bunch of values that are in the decimal range for standard ASCII values. You see numbers that are kind of like 0 to I think it's 127 is the non-extended ASCII values. Then if you decode that, then you get this hidden iframe thing that again exfiltrates the code, the key that's being generated. So what I really like about this is it's sort of plausible at first glance in a way that some of the other examples haven't been plausible. And it's also quite lint proof. So lint is not going to be sufficient for us to always detect underhanded code. It's a good tool, but it's not always sufficient. All right, so those are all the contest entries that I wanted to do. There was about 30 or so total contest entries, and they were all really good. And I would definitely encourage you to look through them, some more of them, to see more about how other people do underhanded code. All of this content, all of the code and the linted versions and so forth, they are up on a Git repository that I put on GitHub publicly, and I'll provide the link to this both in the description in this video, and also there will be a slide for this at the end. So you can go on GitHub and take a closer look at this stuff without having to hunt down the blog article about the contest and all the other resources that I'm referring to here. Okay, so I wanted to talk about a couple other examples that have to do with underhanded code, particularly in a crypto context. So this one is actually from Bitcoin, and this refers to BIP42. BIP42, I think, was written by Peter Willey. And what Peter and maybe some other people observed was there was a problem in a function in the original Satoshi code where in a function called getBlockValue. And what getBlockValue is supposed to do is when you specify a particular block height and also say how much there is in fees for that block, it's supposed to tell you what the value of the block is that's being given to the miner. And it had a problem where there was an integer overflow. There was a variable that was an int 64 underscore t variable. That's a 64-bit integer. And so when we got to a sufficient height, this would you could have a rollover, and so the block subsidy is supposed to start out with 50 bitcoins at the inception of the blockchain, and then approximately every 4 years that's supposed to be halved. We call that the halving, or the more exciting version of that is the halvening. And so that keeps getting halved until it hits 0, and it's supposed to stay at 0 after that. But what Peter noticed was actually when you get to 210,000 times 64 blocks, it rolls over because of the integer overflow, goes back to 50 Bitcoin. And this pattern repeats indefinitely. And so instead of having a supply of 21 million coins for the lifetime of the currency, you have an infinite supply because it keeps rolling back over to 50 Bitcoin every once in a while. This would only be triggered in the very, very distant future, but of course they figured, it's better to fix it now and not let this linger on, so they fixed it. So shown here are the two versions that I've just sort of pasted together, written in C++. And so we have the broken version, we have the fixed version. And the fixed version, because it has this extra check to make sure that, if we get up to 64 halvings, then we don't have to, continue using this right shift off operator to figure out the future subsidy value. And so as intended, once it hits block 6,930,000, just stays at 0 Bitcoin. So we could imagine this being translated into JavaScript. And I want to point out two things here. One is that JavaScript has the same kind of problems where there are numbers that have a maximum quantity to them. And if they get overflown, then they will just roll over to some lower value. And likewise, you can have a minimum value for this stuff as well. And JavaScript will not complain. It won't segfault. It won't throw an error or anything like that. It'll just happily, convert to the correct value for you because it's trying to be helpful. And so this is still a problem. If we look at, if you sort of literally ported the C++ code over to JavaScript, even the fixed version would still have a problem. Rather than having it doing this rollover infinitely, it would only do it once because the problem here is that the right shift operator, if you look up the ECMA script definition of what that right shift operator does, the right-hand value that you're passing to the operator, that gets cast implicitly to a 32-bit value. And so if you have more than 32 halvings, then you're going to have an integer overflow. And so even in this good version, the literal version porting to JavaScript, it's going to repeat the 50 BTC twice. And still sort of broken. So if we think about how we might try to fix these kind of problems in JavaScript, there's a couple approaches that I might recommend. One would be to say, okay, well, whenever you have code that, for example, has a right shift bitwise operator, right? It's kind of an unusual, complicated thing. Let's make sure that we really understand exactly what this is doing. So we would look up the definition in ECMA script and we would see, okay, well, there is a maximum to the value that you can right shift, and there's also a maximum to what degree it can be shifted. And so we'll just look up those two max values. One is like the safe integer value for JavaScript, and the other one is sort of the max for that right hand expression for the right shift operator. And if these numbers that we're going to pass to it ever exceed that, we're just going to throw some kind of error. And, hopefully somewhere down the chain, we're going to gracefully handle that condition. Now, you wouldn't actually want to do this in Bitcoin, of course, because what would happen is you would get up to some particular block height, and then everyone's clients would just throw an error, and the whole entire network would just crash and grind to a halt. So another way that you could try to approach this is to say, well, okay, we know that the built-in types in JavaScript, such as number, have some limitations. So let's use a class that does not have a limitation. It can kind of use arbitrarily precise, large arithmetic operators and values. And so on the right-hand side here, we have an example of what that might look like. This is using Node.js's big integer class. And so we're converting everything into big integer. Now, in some very, very extreme value of the halvings variable, you could still actually get to like a very high value where JavaScript would cast it over to infinity. So you could even conceivably check for that, but this might be after the heat death of the universe or something. It's some very, very large number, given that halvings only happen every 4 years. But I just thought I would point it out that even in the case of using a class that's supposed to do very, very big arithmetic, well, some of these functions do have limitations on like the absolute maximum value that you can get with them. So be aware of that. But otherwise, this example is pretty clean, it's pretty short. It's just using this class that can deal with much, much larger numbers, and that deals with the integer overflow problem. So some general patterns that you can use for dealing with problems such as this. Note that arithmetic is evil. There's lots of things that can go wrong with arithmetic. Many of the very significant zero-day vulnerabilities that have happened in software over the last several decades have to do with arithmetic. And so it's very important that you carefully review arithmetic, make sure you fully understand what exactly is happening with the code, what are the conditions in which something could go wrong, and how are you dealing with those possible conditions. And the way that you can figure out the limitations is by looking at the specification for ECMA script. Seems like right now they're putting out a new ECMA script version about once per year, and they're stuffing it into browsers, so you have to keep updating this every once in a while, although I bet the specification doesn't change a ton from year to year. But you would refer to these specifications, especially for these arithmetic operators, and check out what could kind of go wrong there. Some other basic strategies for developing software to deal with this. One is to try to test these kind of boundary conditions pre-deployment. So maybe you would have unit tests related to this. And in this case, you would want to make sure that whenever you get into one of these extreme conditions, you're explicitly defining what the function should return or what kind of error they should raise or whatever it is, rather than just trying to say that something non-standard is supposed to happen. Define specifically what you're expecting and make sure that for all future versions of your code that stays consistent. And I think it also may be worth checking for pathological conditions during execution and making sure that you're failing gracefully. This certainly does dirty up the code by adding a bunch of extra checks and so forth. But for security-sensitive applications, I think this is worth it. All right, the last example that I want to talk about is about attacking compilers. So a popular thing in JavaScript is to use compilers. People love to use compilers. They like to use the compilers to make their code smaller. So minification, for example, is a big thing to compress down the amount of data that's being sent over the wire. To reduce bandwidth requirements for web users, and also it may also optimize the code in some fashion. Compilers certainly do that, and we also love to transpile code, right? Because maybe you don't like JavaScript because JavaScript is so last year. So you want to write everything in CoffeeScript because CoffeeScript is the new hotness. And so then you pass your CoffeeScript through a transpiler that's somehow going to modify the code and turn it into honest JavaScript. And what's supposed to happen is that your code works the same way before and after it is being compiled, right? The whole point of compilers is that they're supposed to change the code in some beneficial fashion, but without making non-beneficial changes to the what's going to be executed. So this attack was dreamed up by Jan, who goes by Bcrypt. She's a fantastic security engineer and researcher, and she took this idea from a POC, like hacker zine thing where they were talking about this in sort of a general context of attacking compilers, and she did it specifically for JavaScript and going after a minification library. So she went after Uglify.js. She went on their GitHub repository and looked through some of the issues there for bugs and try to find a bug that would be good to exploit, such that you could insert something into a victim's code base that once compiled would change what's going to happen when you run the code. And so she found a bug that was later fixed after version 2.4.23. So this is the version that we're targeting. And this bug relates to De Morgan's law, which is a law in in logic and sort of bitwise arithmetic. And so imagine that you had this statement, for example, not A and not B and not C and not D. Well, you can use De Morgan's law to simplify this to move the not operator to the outside, and by doing so you change all of the ands to ors, and if you took these two expressions in JavaScript, you would go from 14 characters to 13 characters. Okay, great. So if we're compressing our code, then we save a little bit of space. Now, this raises the question in JavaScript, what if any of those sub-expressions, A, B, C, or D, has a non-Boolean value? Because JavaScript has this notion of kind of truthiness, right? There's a variety of ways in which we may be trying to evaluate things in a Boolean context, but we're not evaluating Boolean expressions. We're going to implicitly cast those things over to Booleans. So for example, here's Dwight Schrute, and if we try to evaluate his the top statement here, we have false or not zero. Well, false is false. Not zero is the zero gets turned into a false, so that becomes not false becomes true. So that's true, but then we have not true, which is false. And so zero gets implicitly cast to false. Positive numbers like 1, 2, and 3 get converted to true, and so forth. So if we have some kind of weird value, we can imagine that maybe there's a situation in which the compiler understands that it should be flipping some stuff around to apply to Morgan's law, but there's some value that JavaScript is doing an implicit cast to a Boolean, and so it's not really picking up on the fact that something needs to be changed there. And that's exactly what's going to happen. So Jan wrote this little example function that might be used for, let's say, authentication. And so this is our victim application that we're going to target. So we're going to use this compiler bug, and we're going to write some code in our target application such that when we compile it with the targeted compiler, it's going to do something different after that compilation. Now, this is a slightly odd way to write an authentication function, but this is not really the point of the example is not to try to come up with something extremely realistic looking, but to just show like, well, this is sort of in the realm of realistic, and here's how you could, for example, exploit this bug. You'd have to put some more work into it to make it like extremely plausible and not raise any eyebrows for reviewers of the code. So just to give you the lay of the land here, we have a config variable. The config is either initialized or it's not, something to do with timestamps, whatever. You can ignore that for this example, really. Then we have a user object that we'll instantiate one instance of. The user is either invalidated or not, and it has an expiry date on its token, its authorization token. So if we go to line 39, we're creating a user. We're saying that no, the user is not, their token is not yet it's not invalidated per se, but actually there's only 0 time until the token expires, and so effectively this user token has expired, and what should happen is when we run the is token valid function on line 20, we should see, okay, well, let's say the user has a config, okay, good, the user has a token, okay, and then the token doesn't say it's explicitly invalid, but then when we get to line 28, when we call the getTimeLeft function, it's looking at the amount of time between expiration, the current system time, and it sees, oh wait, this is expired. 0 minus some non-zero value, it's going to be 0 or less. So this is expired, and so what should happen is what will be printed to the console is user is not valid. So if we go to the output here, and when we want to run it through Node, we can see the first example. We execute it, and it says user is not valid. Okay, great. That's what should happen. Now, when we run it through that particular version of Uglify.js, and there are instructions on the GitHub repos to do this yourself if you want to, but also the the minified version is also already there if you don't want to bother. When we run it through that, oh shoot, De Morgan's lie kind of screws it up and it says the user is valid. And if you want to look at the minified version, you can kind of see it's pretty obvious where things sort of went wrong. What to do with the token expiry. So this is a pretty cool way of attacking applications, and there's various strengths and weaknesses to it. One of the strengths is that this is a potentially more targeted way to go about attacking a victim. The reason being that, let's say you changed some library, you inserted some attack code in there, and you're attacking a particular compiler version as well. Well, then you're only going to impact the cross-section of users who are both using that library and using that compiler. And that might be much smaller than the number of people who are just using the library. And generally, more targeted zero-day exploits are going to take longer to detect and to fix. And so that might be a good thing for the health of your 0 day as an attacker. It's also very difficult to detect just from the source code. If we go back one slide to the example, we can kind of see, okay, well, this particular example, it's a little bit janky looking. Like, why would you do not config? That's a very odd way of saying things. But we could try to make it more realistic. And just by looking at it, it's not very obvious that someone is doing something weird with the compiler or whatever, right? And also a lot of peer reviewers, when they're looking over the code, they're not thinking about the full chain, the full supply chain of the code, and like where is the code being pulled down from, what is it being combined to, and particularly like compile time changes. That's just something that typically we maybe mentally check out of. We're not thinking about compilation as a particular vector of exploit. So this could be a way to be very sneaky and make it hard to detect at the source code level. On the other hand, it's a little bit more fragile in the sense that if you're a victim who you're trying to attack, if ever the code gets compiled with a new version of the compiler that sort of fixes the bug that you exploited, well, then it breaks the exploit. And so it does make it a little bit more fragile from that point. As far as plausible deniability goes, I think it's sort of a mixed bag. It really depends on the sophistication of the compiler bug and also how you've expressed it in your target application. And so you could imagine some scenarios in which this might have plausible deniability or it might not. I think for this particular example, if we went back and look at the code after the fact, it would be somewhat obvious that this compiler bug was being exploited, and we would probably be very, very suspicious at best of the programmer who inserted those particular lines into the code and want to more closely scrutinize what was going on there. All right, so just to wrap up, I wanted to present a few thoughts about how people can try to identify underhanded code and prevent it from getting into their applications. So if you are a peer reviewer of code, if you have coworkers who write code and you look at it before you merge them, if you're a maintainer of an open source library, if you are just a programmer and you are using external libraries and you get some new version of the library that you're pulling in, these are all contexts in which you ought to be doing peer review. And I would submit that it's a very good idea when you're doing peer review of code to have a checklist of things that you're looking for. I think all of us who are doing peer review, we have at least some kind of mental intuitive checklist based on our experience, but I really strongly prefer that we have an explicit one. And this is especially important for trying to evaluate the security of things, because there can be a very high cost to missing some kind of security critical change to code. So here are the things that I would add to your peer review checklist if you don't already have one. Basically, just a series of questions to think about. So first is this code that I'm looking at, does it ever execute code from other sources? Is it pulling down external sources and executing the code? Likewise, if it's somehow self-referencing, as one of the examples that we saw was with referring to a link that's contained in a comment in the code. We want to be aware of that as well. Do I understand all of the arithmetic here that's in this code? As we saw, arithmetic can be a big vector for either malicious or accidental bugs to arise. Does this pass Lint checks? I think that we should start only running code that is completely Lint friendly. This, perhaps prevents some novel things that we could aspire to do with JavaScript, but for security critical stuff, I think it's worth it. Could this create covert channels to leak data? So for example, we are using these image tags and stuff to leak data. Well, if we're looking through a code and it creates an image tag or some other kind of reference that could create external traffic, or I mean, if it's a type of program that's not just interacting with network traffic, but other kinds of external channels of information, file system, for example, we want to think carefully about whether this could create a covert channel to leak data, or if not that, then to pull in data or external code, as we mentioned before. Are the variable values clear? Are we, as I read through this code and I look at the different variables that are declared and used, do I understand what the values are going to be? I think that's important. Are the variable types consistent through execution? We saw a few examples that play around with changing the variable type over time through implicit casts, or somehow obscuring what kind of type of variable we're going to have. JavaScript is typeless, and so it's happy to store any kind of data in any kind of variable. And so this should be very, very clear as you're reading through the code. And if it's not clear, it merits additional scrutiny. And generally speaking, you should not be reusing the same variable names to refer to multiple types of data. Maybe the odd exception is you have a function that returns a number or it returns some kind of null value in the event that it can't return the number that it wanted to, but then that should immediately be checked for this should be made clear in the prototype of the function, saying, okay, this is what's going to return this or null, and make sure that all callers of that function are explicitly checking for those different conditions. Does this code clearly delineate global and local scope? We saw with my example where we had the arguments variable, I was playing with global and local scope. There was arguments when it was in the functions, it was strictly local, and I was misleading the reader about whether it was going to be global or local scope. There's another great example I didn't put in this talk just due to time restrictions, but there was another example from the same contest. I think it might have been the runner-up, where they had a bunch of variable names that were had Unicode characters in them, and so they looked very, very, very similar when you're reading through the code. But there was like a funny looking E that was Scandinavian E or something like that. And just by the by, if you ran it through a linter, it would choke on the Unicode characters in the variable names, because it doesn't want to see any kind of Unicode strings in the source code, which is a good idea. And lastly, have I reviewed the network traffic? If I actually taken this code and run it in some environment and opened up my network tab or whatever it is, just to see if anything funny or unexpected is going on. Just a few other things to look out for. So, a lot of the examples that we looked at had kind of an odd smell to the code. And by that, I mean they had some suspicious characteristics to them. So they made use of weird conventions in JavaScript, like the tilde operator, magic numbers. If you ever see magic numbers, there may be good reasons for that, but it's time for you to go ahead and look up what that reason is, right? Don't just see a number and be like, oh, well, I'm sure someone made sure that this is the right number. If you see references to strange IP addresses or domains, and there are various ways that you can represent those things, that's important to note. If you have unused variables or dead code, also, those are two hints that something off may be happening, that the author of the code may be trying to mislead you about what the code is doing. And also the use of non-standard or old library libraries in the code. They may be trying to exploit some bug that they know about by using it in the code. So be cautious about that. A few basic tools that you can use to detect this kind of stuff. We mentioned Lint before. Debugging, I think, is a good idea, right? So you run the code in your browser or the Node command line application, whatever is appropriate for your application. You can insert console.log statements in there if you want to. You can use the debugger statement, which works well in browsers. So, for example, if you have some code, you're trying to figure out what it does, you can take a portion of it, put it into JS Fiddle, change it however you need to change it to make it work on its own without all of the other code that's in there. And then you can insert these debugger statements, and what will happen when your browser gets to one of those, it will stop and start debugging it. And Chrome at least has like a really cool sweet JavaScript debugger. Well, where every time it hits a breakpoint, it shows all of the values of the variables like inline in the code, and it shows you like the stack of variables, and you can kind of step through the program using these debuggers. Firebug used to be the go-to tool for this, and there was an extension for Firefox that would help you step through code. So that is very useful to make sure that as you're going through a function or as you're going through a loop or whatever, you can look at what the final state is of these things, but there may be something going on in the meantime that is somehow tricky. And so you may find it helpful to just kind of step through it very, very slowly, one line at a time if necessary, assuming that there are not too many iterations of the loop or whatever, to make it practical to see what exactly is going on. I would also say that it's very helpful for browser code that's going to be doing network stuff to use a network inspection proxy. There are network tools built into browsers these days. They're part of like the built-in developer tools. They're okay. I don't really love them. I don't usually use them. What I'll typically do is I will set an HTTP proxy for in the browser and use another tool to actually capture and modify and inspect data, and you can capture it before it goes out to the web server if you want to. That Burp Suite does that, for example, in what you would call intercept mode. So Burp Suite is a good tool for that. They have a free version which is very flexible and very, very good as a proxy tool. There's also Fiddler, which is free and open source. Same thing for OpenWasp Zap. Zap maybe even has a little bit better capacity for WebSockets and some other stuff. And then you may also have to deal with some network protocols that are lower level or just sort of outside the browser. So you can look at TCP dump, Wireshark, and there's a million zillion network proxies out there specialized for various protocols as well. So you have those. Some other general defense in depth things that you can do to mitigate the effects of underhanded code. One is a social concern, which is accountability. So if you're only using libraries that are projects that accept code from people that have a reputation, well, then if they ever find that the person introduced some awful bug, then then they suffer some negative consequences for it. That's great. It's going to be a deterrent of some sort for writing underhanded code, perhaps. You want to use dependencies that are up to date. If you're writing Node code and you're not using snick.io already or some comparable service, you should definitely start using it. Kind of scan your code and figure out, okay, well, based on the requirements that you have for your Node code, which versions of libraries are you actually pulling down? Do they have any known vulnerabilities in them, and so forth? Also, when dependencies change, when they release new versions, rather than just saying in your package.json list of dependencies, well, I'll take 1.x.x of library Z, maybe specify lock it down to a particular version of library Z rather than just pulling in all sorts of changes and never reviewing them. That's kind of dangerous, as we have seen with some of the stuff going on with Node dependencies lately. And it may also be worthwhile to have your own private copy of some of these repositories, just to make sure that you're not there's not a discrepancy between your private copy and the public one, and there's no tampering of the repositories going on for your libraries. I also want to draw people's attention to a really cool technique. It's based on this paper that people wrote circa 2012. Called Privilege Separation for HTML5 Applications. That's the name of the white paper. And in it, they sort of talked about how web browsers these days, browser applications, they are pulling in code from a lot of different sources, and there's different levels of trust with all these different sources. But the way that we tend to handle these stuff these days is it just gets pasted into one giant global context, and if any part of our code gets compromised, well, then we're kind of screwed, because it can just kind of have unlimited access to all the JavaScript stuff going on in our application, and has access to the DOM and all kinds of nasty stuff. So their idea was, let's instead use some other stuff going on in the browser, leverage some underutilized stuff going on in the browser to secure this stuff. And so one of the things that we have are sandboxed iframes, which have a fairly strict standard origin policy that's applied to them. And what we'll do is we'll load when we open our main window, it's going to load this framework for privilege separation, and then we'll take the different pieces of code that we need, we'll put them on different, let's say, subdomains or port numbers or whatever to break standard origin policy, same origin policy, and we'll load them in child iframes, and then the child iframes will only be able to access the parent and access each other through the parent through these very mediated, controlled messages that are being passed back and forth, rather than making direct calls to one another as pieces of JavaScript running in a global context. And so I think this is a pretty powerful idea. I think I've been told that they're using it at Dropbox, and so I think this could be a powerful way to mitigate something going wrong in one area of the code, to make sure that it doesn't break out and get into too many other areas of the code as well in a browser-based context. You also want to limit novelty in your code, so use standard libraries. Make sure, in particular in a crypto context, you want to use standard libraries. We know that home-baked, obscure kind of crypto code is often broken and has serious flaws, so don't do that. And then just basic AppSec stuff, right? So input, output, validation and encoding is going to, even if there's a problem that happens with your code, some of the stuff may prevent it from getting completely out of hand. And there's some other controls built into the browser that may be useful. So content security policy could potentially be helpful there. So for example, if you had underhanded code that snuck in, but it was trying to pull some code down from an external source that's not whitelisted in your content security policy, and therefore is being excluded, then maybe that sort of breaks what the attacker was trying to do. So just some basic stuff. It's not it's not all encompassing defenses. You still have to do all the other stuff that we talked about, but this may be helpful in some sense. So that's it. I will just briefly mention some of the things that I referenced and other resources you can check out. So there's a number of contests that deal with underhanded code. There's one for JavaScript, PowerShell, C, and one for crypto as well. The crypto one is quite interesting. I would have loved to pull some of those examples in here, but they were sufficiently complicated that I couldn't figure out a way to talk about them quickly. There's a book on how to be a complete arsehole with bad JavaScript, talking about the funny things going on in JavaScript. And if you Google for WTF.js, there's a number of different resources talking about all the quirks of JavaScript, and these are all things that an attacker could try to leverage to make their JavaScript do something unexpected. I'd like to acknowledge and thank Peter Jarek for holding the JavaScript misdirection contest. That was a big inspiration for this presentation. Also, we talked about the Goto fail bug, and go to gotofail.com for that. And awesome security researcher who you should follow on Twitter at bcrypt, Jan. She wrote the article about backdooring your JavaScript using minifier bugs. And if you want to get in contact with me, my Twitter handle is Kristov Atlas. On Twitter, I have a blog, kristovatlas.com, where I mostly blog about various things to do with Bitcoin. And I'm a member of the Open Bitcoin Privacy Project. You can find our GitHub repo there. And all of the materials for today's talk are up on GitHub at github.com/kristovatlas/underhanded JS-crypto. And that's it. Thanks so much for watching, and I'd love to hear your feedback and your ideas about how to write underhanded JavaScript code and how to defend against this stuff.